chapter, but we're going to take a look at liquids, solids, and intermolecular forces. And I think from a chemistry standpoint, this is probably one of the topics that is most applicable regardless of what you're going to go on and study. So it doesn't matter whether you're going to be a marine science major or a kinesiology major or a biology major or a computer science major. The topics that we're going to be covering for chapter 10 have a pretty significant impact in each of those fields. So I think that the focus really as we finish out the semester is on this idea of ownership or the self-regulation of learning. So you are in this space where you're transitioning to more and more responsibility, both for how you study and what you study. And that's only going to increase, I think, as you continue in your academic pathway. So by the time you're taking 400 level elective courses, there will be much less direct instruction in terms of do this or what the structure of the activities look like, and much more choice on your part in terms of how you engage in solving problems. So our goal by the end of the semester is to equip you with strategies that will allow you to be effective when you study. And so I think, especially as we move into studying for final exams, I really want you to feel comfortable taking advantage of the different strategies and exploring which ones are the best fit for you. Okay, we're going to take a look today at intermolecular forces versus intramolecular forces. And I think that I was looking for an image that would help us make sense of those ideas, and this was a pretty solid one. So when we talk about forces, we're going to think about the strength of those forces. And so that strength is usually dependent upon distance. We're also going to think about whether or not those are forces that are between molecules or forces within molecules. So somewhere in your notes, it's going to be really important that you make the distinction between inter, which are the forces between two molecules, and intra, which are the forces within molecules. So we're going to explore this with at least the spaces that you already have prior knowledge. So for example, we've talked about ionic and covalent bonds. Those are bonds that are fairly familiar to you. So for our first exercise, I want you to come up with at least 2 examples of ions and 2 examples of covalent bonds. You can look back in your notes if that's helpful to you. You can use other resources like your textbook or your computer, but I need you to come up with at least 2 examples of ionic bonds and 2 examples of covalent bonds. And we'll go with maybe 3 examples from folks before we move on. Ooh, Arlene had a great observation in the chat. Intercollegiate athletics are between 2 campuses, like us versus San Jose, and intramural sports are teams on a campus that compete to see who is best. Oh, nice. That's a great analogy. Thanks, Arlene. That's a great way to think about it. All right, let's see if we can get some examples. Can anyone give me an example of an ionic bond? You can do it in the chat, or you can unmute and share it with the group. Ooh, nice. Thanks, Heba. NaCl is a great example of an ionic bond. Na is our cation, and chloride is our anion. Can I get an example of a covalent bond or another ionic bond? Oh, thanks, Deja. So NH3, oh, thanks, Faraya. HCl, CO2, those are all great examples of covalent bonds. HCl is a little unique in that it's covalent, but it really behaves like an ionic bond. So it's a great example of how there's a spectrum. So those are great examples for us to take a look at. So our focus today is with that prior knowledge in mind, we're going to take a look at intermolecular forces, or the forces that are between molecules. And there are 4 that we're going to consider. We're going to look at dispersion forces. You may have already heard of these. Sometimes they're referred to as London forces. We're going to look at dipole-dipole, ion dipole, and then hydrogen bonding. And I think this is a really great question. Somebody asked this the other day. They're like, is it possible that something doesn't have or experience any forces between molecules? And the answer to that is within this box where it says zero attraction is only possible with ideal gases. And I will put the caveat there, it's really only possible with ideal gases and a lot of space, because even in a small space, you're going to have some Brownian motion that will cause interactions between your ideal gases. So one of the other points that we're going to make sure that we're attentive to is the fact that this scale in terms of force is with respect to, right, kilojoules per mole. And so if we're thinking about that, it's really important that we make the distinction that we're thinking about on a per mole basis. So the amount that we have really would matter. Okay. So important that we define our terms here. Intermolecular forces are thought to be attractive forces. So they're weaker for 2 reasons. They result from interactions between partial charges. So if you remember, we use the partial charge delta positive and delta negative, and they act over longer distances than bond lengths. So a good way to think about this is that you can have intermolecular forces that are attractive even if molecules aren't right next to each other. So they can act over slightly different distances than what we think of in terms of bond lengths. The other piece that is useful for us to think about is this idea of attractive forces versus kinetic energy. So when we think about the physical state of molecules, whether it's a solid, a gas, or a liquid, depends on which is greater. Is the internal kinetic energy of the molecule greater, right? Then it's going to have more movement. Or are the intermolecular forces greater, in which case they're going to hold or stick together closer? One way that we can see this are substances that have strong intermolecular forces tend to have higher boiling points. So as your next exercise, I want you to draw at least 5 water molecules, put them relatively close together. And I want you to think about the partial positive and partial negative charges. Where would you put those partial positive and partial negative charges? And if you're like, oh, I don't know how to do that, think about the electronegativity of your oxygen versus your hydrogen. Which is more electronegative, the O or the H? So you're going to draw your hydrogen bonds. Right, so you have an H2O molecule, and so your partial positive charge is going to be on your hydrogen. Your partial negative charge is going to be on your oxygen. And if you think about how those might tumble, right, in space, they're probably going to orient towards each other where the positives are drawn towards the negatives. And so if we think about the behavior of water when it's a solid, probably that organization is a little bit more rigid. If we think about when it's a liquid, that organization has a little bit more of a tendency to kind of break and reform. So that's what we think of when we see liquid water. And then when it's a gas, right, those water molecules are separate, right, and they only, right, through kinetic energy bump or tumble into each other. So Mackenzie had a great question. Ooh, is the partial positive on both H atoms? Yeah, you're correct. So both of your hydrogen atoms are going to have a partial positive charge. And then it's your oxygen that's going to have a partial negative charge. And again, the reason for that is that the electronegativity of hydrogen is less than the electronegativity of oxygen. So we're going to come back to this idea of the interactions between molecules with respect to water in just a moment. So hold that thought in your notes, put your finger there, we'll come back to it in just one moment. Before we go on though, we want to talk a little bit about this idea of a dipole moment. So a dipole is the interaction between charges. And that interaction between charges is really governed by the distance between those charges. So a dipole moment is separated charge and the distance between those charges. So if you're thinking about a dipole, it's anytime you have a partial positive charge and a partial negative charge, or an actual positive charge and an actual negative charge, and the distance that is between the center of those charges. Part of the reason why it's important to be able to talk about dipole moments is because these exist for almost all materials. And so you could calculate what the dipole moment is, say, for example, in cotton. And maybe that's part of the reason why t-shirt material has the properties that it does. Or you could think about the dipole moment that exists, say, for example, in aluminum foil, and some of the properties that it has. So when we're thinking about these intermolecular forces, the reason why we're curious about them is because they impact the material properties of just about everything that we would study. So if you think about your dipole moments then and symmetry, we talked about this example of water molecules. So Heba gave the example of a carbon dioxide molecule that's shown on the left. And what I want you to notice is you have the partial negatives on your oxygens and you have a partial positive on your carbon. But here's the piece of that that's most interesting. Do you notice that the direction of the bond dipoles, and when we draw these, it's important that the head of the arrow points toward the more electronegative atom, and the tail of the arrow, or the cross of the arrow, points towards the less electronegative atom. So take a moment and draw carbon dioxide in your notes. This is a molecule that we've already had lots of practice drawing Lewis structures and determining electron and molecular geometry for. And so we know that carbon dioxide is going to be linear. It's linear because it has two double bonds to oxygen. And if we think about drawing our bond dipoles, they point in opposite directions. And so the conclusion that we can draw is that there's no net dipole because this molecule is symmetrical. The dipole moments cancel. But if we compare and contrast carbon dioxide with a water molecule, we're going to notice that our bond dipoles, again, the cross points towards the hydrogen, the tip of the arrow points towards the oxygen. This actually has a molecular dipole because these two arrows don't cancel. In fact, they point and create an overall dipole for the molecule that's drawn in blue here. So this is what we call a net dipole moment. If you've taken physics, then you've probably talked about vectors. If you haven't taken physics, that's okay. That's something to look forward to. The idea of a vector is it's something that has a specific orientation with respect to position. And so we've been talking for the past 2 chapters or so about the 3-dimensional nature of molecules. And so bond dipoles point in a given direction. In this case, they both point towards the oxygen. And because they both point in that direction, we're going to add those 2 dipoles together to give us an overall net that's pointing towards the oxygen. So if we're thinking about our dipole moments, it's something that is additive as a property, and it's something that's dependent upon symmetry. So if a molecule is symmetrical and I have a bond dipole, then when I add those 2 together, if they point in opposite directions, they're going to cancel, so there won't be a net dipole. But if I have a molecule where I have symmetry but it doesn't cancel, it's going to be additive and give an overall net dipole. So I want you to take a moment before we transition and write a claim evidence reasoning statement. So for this example, make the claim that water has a molecular dipole what's the evidence for that and your reasoning. Or make the claim that carbon dioxide does not have a net dipole moment. What's the evidence and the reasoning for that? So take a moment and in your notes, construct a claim evidence reasoning statement. So Mackenzie had a really great question about a net charge arrow. So in this case, it's not so much charge because water is actually a neutral molecule. So overall, there's no charge. And the reason why we know there's no charge is because we can actually calculate the formal charges for both oxygen and hydrogen. So if we think about that for a moment, we know that oxygen has 6 valence electrons, and we know that it has 2 bonds, and what's not shown here are the 2 lone pairs, but they exist. So 4 plus 2, so 6 minus 4 plus 2 is something that we've often calculated for oxygen, and that's a net neutral charge of 0. And then hydrogen in this case only has 1 valence electron and 1 bond, so it's also net neutral. But I think Mackenzie is on the right track because the arrows that we're drawing here are what we call partial charge or induced charge, which is to say that we recognize that oxygen and hydrogen have different electronegativities. So the overall arrows that we're using here are to say that the electron distribution for water is not the same. So when we have electrons in this molecule, they have a tendency to be found around the oxygen and fewer around the hydrogen. So a molecular dipole is saying, oh, there's a difference in electronegativity between my oxygen and hydrogen atoms. And because I have 2 of those bonds, that's going to be a cumulative or an additive effect. So I'm going to have more negative or electrons towards my oxygen, so more induced charge towards oxygen than I do towards hydrogen. So a good way to think about this is it is not the same as the charge that we see for ions, but it's similar. So we see induced charge here, or partial charges, which has to do with the difference in electronegativity between atoms. Okay, so I've given a bunch of examples here, and I want you to choose at least 3 of these to draw in your notes. So the dipole moments are already drawn. Notice a net dipole is shown in pink. So if there is a net dipole for the molecules, it's drawn in pink. There are molecules that, because of their symmetry, have no net dipole. So those are molecules that only have the black arrows and no pink arrows. So can you take a moment? So Heba's on the right track. She's asking, is this the difference between polar and non-polar covalent bonds? The answer is yes. When we have induced dipole moments, that's going to be the uneven sharing of electrons, which is what makes molecules polar. So yes, you were on the right track. We're going to talk about polarity on Wednesday. But for now, I'd like for you to go ahead and draw at least 3 of these molecules. So you're used to drawing Lewis structures now. And I want you to think about the direction that the arrows point. Can you make sense of the way those arrows are drawn based on your periodic table? Hopefully, you recognize that the least electronegative Atom is typically in the center, although there are some exceptions. We know that, for example, hydrogen can never be our central atom, even if it is our least electronegative. So you want to be careful in the way that you are drawing your arrows. And you want to make sure that the head of the arrow, or the pointy part of the arrow, is what points toward the most electronegative. And the cross, or the tail of the arrow, is what points towards the least electronegative. So we're going to hang here for a moment so that you can draw out at least 3 of these examples. One of the things that I want you to notice about the way these molecules are drawn is the following. You are familiar with how to draw Lewis structures, which means that you know how to draw bonds and lone pairs. These structures are shorthand versions of the molecules in that they don't include lone pairs. Part of your skill as a scientist is being able to interpret information. So when something is missing, right, to realize that it's there even if it's not represented in the model. In this case, when we draw these molecules, it's a simplification to make it just a little bit faster for us to draw them, but it's still feasible for us to make sense of the behavior of these molecules because of their arrows. And so here's the thing that I want you to notice. For example, carbon tetrachloride has no net dipole. The reason for that is because this molecule in 3 dimensions, right, is something that has no net because it's symmetrical. So while it's drawn as though it's flat on the plane of the paper, right, it could also be drawn with the wedges and dashes that you see for chloroform, which is the molecule next to it. So you could draw a wedge and a dash, and then this molecule becomes something that's truly, sorry, that was Wiley shaking to get rid of her collar, which she's trying to fuss off. My puppy dog loves to move, so sorry for the jingling and jangling. Okay, so that wedge and dash is something that we can use to represent the 3-dimensional nature of a molecule. All of these molecules, with the exception of BCl3 and CH2O and HCl, so the 3 that are on the left, all of these molecules are going to be 3-dimensional. So when we think about their net dipoles canceling, we actually have to imagine that in 3-dimensional space. Or, say for example, if you were taking an organic chemistry class, you might actually build it with a model to be able to see it. And if you're like, ooh, it would be really helpful to see that in 3D, then my suggestion is that you use the molecule simulator that we've been using with our electron and molecular geometry to help you see that. So if you're looking at this and you're like, I just don't see in 3 dimensions how it cancels, then I highly recommend you build a model because it will make it much more accessible to make sense of that. So our takeaway from this is that we are going to be able to draw arrows. The arrows that we draw are going to tell us something about the difference in electronegativity between atoms. And again, if we need to, you'll be using your periodic table in order to be able to do that. And then the really cool part about this is that we're going to look at the sum of all of those arrows together and make a determination about whether or not there's an overall dipole moment. So why does that matter? Well, we've just talked about this idea of a dipole moment, and now we're going to start thinking about how dipole moments influence the behavior of atoms. So larger electron clouds have larger, what we call instantaneous dipoles, and stronger dispersion forces. So the dispersion force is really whether or not a molecule in a moment can create an electron dipole, and that dipole then can influence the behavior of other electrons or other atoms that are near it. So a good way to think about this is that the size of the electron cloud is going to increase with molar mass. So it's the charge interactions that hold things together, not gravity. So it's really the London dispersion forces between molecules that hold them together. So if I think about noble gases, for example, and their molar masses, the larger the noble gas, the greater the molar mass, the higher its boiling point is going to be. So if we look at the behavior of, say, for example, gases, and when they're a liquid versus when they're a gas, what determines the amount of energy that I have to put in order to change a liquid into a gas is its boiling point. So that's the temperature at which a gas molecule can escape the liquid molecules. And so that's going to be dependent upon London dispersion forces, or in this case, the size of the electron cloud and molar mass. So this is a really good example of a practical application of intermolecular forces, or London dispersion forces. London forces also depend on contact area. So if I have a really small contact area, I'm going to have the weakest possible attraction. If I have less surface area, then there's going to be less attraction. But if I have a large contact area, then I have a strong attraction. And so here I have neopentane, isopentane, and N-pentane. And so you're going to learn about this in Chem 111, but pentane means 5 carbons, and you can actually see the 5 carbons because they're the gray molecules, or sorry, they're the gray atoms in the molecules. And then the hydrogens that are bonded to those carbons are the white. So this is a ball or bubble model. And so this kind of shows you the distribution of electrons. In this case, there are single electrons that occupy the hydrogens. Carbon, we know, has 4 valence electrons. And so you can actually see the contact area and the difference between neopentane, where it still has 5 carbons, but they're very close together, versus isopentane that has 5 carbons and they're a little bit more spread out, versus N-pentane, where these are carbons that are connected literally in a linear form. And so they have much more surface area or contact area because they're spread out. So if I think about this between molecules with the same force type, so in this case, the force for each of these molecules is only London dispersion, and the same chemical formula, which in this case is true, right? If I think about N-pentane, I could count, it has C5, right? N is my carbon, and then my hydrogens would be 12 because it's completely saturated. So it's 2N plus 2, so 2 times 5 plus 2 gives me the number of hydrogens that I would see for pentane. The only thing that's different in these molecules then is the different shape. And so the difference in my shape is what's going to determine the difference or the significance of my London or my dispersion forces. And I can see that because of the difference in boiling point. So neopentane has a boiling point of 9.5 degrees Celsius, whereas isopentane has a boiling point of 27 degrees Celsius. N-pentane, which has a much larger surface area, is going to have a boiling point of 36 degrees Celsius. So this really matters because if I think about each of these molecules, their boiling point is going to be determined based on their surface area. So mass and surface area are what are going to determine the effect of my London forces. So if I had a molecule, let's say butane, that had 4 carbons, can you draw butane at least 2 different ways? So take a moment and draw butane, 4 carbons, and then give each of those carbons enough hydrogen so that it has a complete octet. What would that look like? So you could have linear butane, right? So that's 4 carbons in a straight row with hydrogens attached. So if I think about that, it would be C4H10. There are 2 different ways that you could draw butane, at least. Right? So if it wasn't linear, what else could it look like? And then of those 2, which would you predict would have the higher boiling point? So if we think about the inference that we have so far, we would predict that butane in its linear form, or N-butane, would have the higher boiling point. So this is an example of the type of questions that you might have to answer associated with intermolecular forces. Okay, so here's the big idea associated with London or dispersion forces. They are the most common forces, they're everywhere, and they're the weakest. So every atom, ion, molecule can have an instantaneous dipole. This idea of in space you can induce a dipole, right? Or your neighbor can induce one in you. So because this is the weakest intermolecular force, and we are usually interested in the strongest force that's present, there are lots of molecules for whom this is the only force that exists. So it's the only force between, say, for example, molecules that are made up of carbons and hydrogens only. So we call those molecules hydrocarbons. But London dispersion forces, say, for example, are the only forces that are present between butane molecules or pentane molecules. So anything that is only carbons and hydrogens typically has London or dispersion forces as the only force that's in play. But there are other forces that we're going to take a look at as well. So we're also going to take a look at dipole-dipole interactions. So dipole-dipole interactions occur between what we call permanent dipoles. These are generally stronger than London forces. So you'll notice for a dipole-dipole interaction, there is a difference in electronegativity or a difference in charge. If you were to look at the electronegativity scale, the difference between hydrogen and carbon is pretty small. But the difference between oxygen and hydrogen, or oxygen and carbon, in terms of its electronegativity is pretty significant. So if we think about the positive end of a polar molecule being attracted to the negative end of its neighbor, this is a good way to envision a dipole-dipole interaction. So I have partial charges that I can assign to a molecule based on its electronegativity or the trend of electronegativity in a periodic table. Because I can assign that partial positive and partial negative to a molecule, then they're going to orient in space to create a dipole-dipole interaction. So the dipole of one molecule will interact with the dipole of another molecule. So take a moment and draw 2 water molecules. And in this case, I want you to think about where your partial negative charge is and where your partial positive charge is. When we think about water molecules, they actually have a stronger force even than the dipole-dipole interactions that we're referencing here, because they have what we call hydrogen bonding. And that's a very special kind of dipole interaction that we're going to talk about in just a moment. But they're the easiest, I think, example to remember, because you know that oxygen is going to have a partial negative charge and hydrogen will have a partial positive charge. So we're going to look at some examples of different strengths of dipoles and their interaction with each other. So molecules with larger dipoles have stronger intermolecular forces and higher boiling points. So a good way to think about that, you can actually see it by analyzing the table shown here. So if we look at propane, its mass, its molar mass is 44 grams per mole, compared to, if we look at something like dimethyl ether, right, which it has a molar mass of 46. But you're going to notice, right, the larger the dipole, the stronger the intermolecular force. So you can actually see here that even though their molar masses are relatively similar, one of the things that happens is there's a difference in boiling point because of the dipole moment. So in this case, you're like, well, what dipole moment? Where does that exist? Well, if you think about your dipole moment that we would draw for propane, right, this has very small dipole moments because there's not a significant difference in electronegativity between the carbons and hydrogens. So that's really falling within the realm of London dispersion forces. Whereas there is a difference in dipole moment for dimethyl ether, or there is a difference in dipole moment for ethylene oxide, where because there is an oxygen present, and that's much more electronegative, it's going to draw, right, or create that dipole. And then acetaldehyde and acetonitrile have even larger dipole moments, even though in the case of acetonitrile, its molar mass is actually smaller than that of, say, for example, propane. So because you have this pull of electrons between the carbon and the nitrogen, in the case of acetonitrile, it's going to create a larger dipole moment. So we have to be really careful. Just because something has the larger molar mass doesn't mean that it's always going to have the greater boiling point. It really actually depends on whether or not there's a difference in electronegativity. All right, we're going to talk about hydrogen bonding, which is the strongest of the dipole-dipole interactions. So this only occurs within molecules that contain OH bonds, FH bonds, and NH bonds. Other molecules might experience dipole-dipole interactions, but that's not the same thing as a hydrogen bond. And we have to be really careful because we talk about hydrogen bonds, but they are not the same thing as a covalent bond or an ionic bond. They're actually much weaker. And because of that weakness, it's really important that we understand both how they form and when they form and what they do. So anytime you see a molecule that has OHs, FHs, or NHs, there should be a little alarm bell in your head that's ringing and saying, oh, those probably experience hydrogen bonding interactions. Okay, so if we're thinking about this molecule then, we want to be thinking about a couple of things. If I'm looking here, it's clear that I have oxygens, I have carbons, and I have hydrogens. And it looks like from the way this is drawn that I have at least one oxygen, two carbons, and a bunch of hydrogens. My hydrogen bond is always going to be between the hydrogen of one molecule and, in this case, the oxygen or the electronegative of another molecule. So we draw our hydrogen bonds dashed or as dots because that's how we make the distinction between a strong bond like a covalent bond that's drawn with a solid line and the weakness of a hydrogen bond. So hydrogen bonds are the strongest of the intermolecular forces, but they're nowhere near as strong as the covalent bonds. So why do we care about hydrogen bonding? Well, it's still an intermolecular force and not a chemical bond, but it is the strongest attractive force for a pure substance. So let's take a moment and I want you to analyze the diagram or the graph that you see in front of you. So what we see here are trends for boiling point for group 6A and group 4A atoms. So in this case, it's the molecules that are formed when group 4A bonds with hydrogen, and the molecules that are formed when group 6A bonds with hydrogen. And you're going to notice that for the group 6A, right, we have a general trend that is increasing. And for the group 4A, though, we have this unusual and really striking behavior of water. And that's because water can form hydrogen bonds, whereas H2S, H2SE, and H2TE are less likely to form those strong hydrogen bonds. So let's talk about what are some of the behaviors that we see in terms of hydrogen bonding with respect to chemistry. And I will say for this class, I do not expect you to be able to give a reason why water has greater hydrogen bonding than H2S or H2SE. That's not a question that I'm going to ask for the context of this class. It's actually outside the scope of what we're learning. But I will expect you to know that hydrogen bonding, such as what is seen in water, is the reason why it has such a high boiling point. So we're going to talk a little bit about properties. Specifically, we're going to talk about surface tension. So liquids tend to minimize their surface area. If you have ever looked at, say, for example, water droplets on a glass or on a surface and wondered, well, why do they even form drops? Why do they form spheres? This is because of surface tension. So they minimize their surface area.
You tie your pippies.
And, right, they really interestingly, right, lower the potential energy. So these intermolecular attractions draw molecules together for the purpose of reducing the amount of energy. So the stronger the intermolecular forces, the higher the surface tension. So if you think about it, right, interacting with only 4 neighbors versus interacting with 6 neighbors is what makes the difference in the behavior of a molecule. So here, right, our sphere, right, is comprised of the way that water would interact with each of its neighbors versus the behavior of water molecules that are at the edges. So when we talk about surface tension, we're talking about the ability of liquids to minimize their surface area or to draw together because of the intermolecular interactions. Another property that we often see is viscosity. So this is the resistance to flow. It's going to decrease with increasing temperature. So I want you to think about something that's a really thick liquid. Go ahead and put at least 3 examples in the chat of thicker liquids. What are some things you think of that have resistance to flow? Ooh, syrup, honey, oil. Right? Those are great examples. And, right, if you think about it, have you ever warmed those substances up and noticed that their thickness changes? They become thinner, easier to pour. So probably my favorite example of this is you can take hot fudge, which is something that folks typically serve on top of ice cream sundaes. And if you heat that up, right, it becomes a little bit thinner and easier to pour. But then as it cools on the ice cream, it thickens again. So this is that resistance to flow or viscosity that you see in syrups or in caramel or molasses or honey. And the reason why they have that property, which I think is so cool, is that it's because of intermolecular forces within the molecules that make up those substances. So the longer the molecule, the greater its tendency to tangle, the greater the viscosity it will have. And so if you increase the number of intermolecular forces that then can occur between molecules in those substances, then you're going to see more viscous solutions. And so if you had to then design a molecule that had less viscosity, you would predict that it would be a molecule that has minimal intermolecular interactions. Now, it'd be tricky to be able to say none, because most of these have at least some intermolecular interactions, but you would be able to design a pretty non-viscous material if you could remove or lessen the amount of intermolecular forces. Capillary action is another great example of a physical property that we see associated with intermolecular forces. So it has this idea of adhesive forces are what attract a liquid to the surface of the tube. So if you think about the inside of a glass tube, there's adhesion or attraction between the forces of the liquid and the wall of the tube. And so these cohesive forces attract the molecules to each other and to the tube. And so in a narrow enough tube, you're actually going to see convex or concave meniscuses based on the attractive forces or capillary action. So in this case, mercury and water have different behaviors. If you were to look in a glass tube and it had a sufficiently narrow enough tube, then you would actually see that water has a meniscus that is concave or dips down, and that mercury has a meniscus that is convex or curves up. And so based on that, you can infer something about the attractive forces of each of these liquids, that they are drawn, say for example, in the case of water, they are drawn to the sidewalls of the tube, and there's a greater adhesive force that's there, whereas the force is less for the mercury, which is the reason why if you've ever seen mercury move, it kind of looks like it's almost slipping or moving really freely. That's because it has less adhesive forces. Okay, so we're going to take a look at the science practices that we've been using so far in terms of asking questions and defining problems, as well as analyzing and interpreting data. And I have a task that I want you to apply your excellent minds to. And so I'm going to show you. So here, right, we've been using a worksheet for our electron and molecular geometry. And you're going to keep that as a reference, but we're actually going to take a look at the, in the email that I sent you, I attached, a worksheet, and we're going to take a look at that worksheet. So find it. So super important, because we're going to take our knowledge and we're going to apply it to assigning intermolecular forces. So we're going to do a couple together as a place to start. And then we're going to come back to this when we have class on Wednesday this week. So what I'd like for you to do is go ahead and do your assignments. I included the answer key because I want you to have a reference that you can check. But before you take a look at the answer key, I really want you to think through a couple of these on your own. So let's do some of these together. So if we think about ammonia and what its structure looks like, if you were to draw that on your whiteboard or in your notes, go ahead and draw the Lewis structure for ammonia. And so in this case, right, we would be able to predict that ammonia certainly is going to have London forces. And if we think about what we talked about in our notes, right, are there any other forces that apply? So we haven't talked about network solid or covalent bonds yet, but you can actually think about that in the sense that your network covalent bonds are really the bonds that exist between molecules. So a good way that you can think about that is, hey, what if I had covalent bonds for this molecule? Where would they show up? And would they be solid? So essentially, between molecules, would I have covalent bonds. And then the ionic crystal, really, that's thinking about, do I have ionic bonds where I have the transfer of electrons? And then the other one that I'm thinking about is, do I have, right, metallic bonds? So this is bonds that exist only in metals or in a sea of electrons. So for these, while they're bonds that we haven't explicitly talked about today, I think there are bonds that you would have some reference for. And so we can at least take a look and start to think about whether or not they would be bonds that apply in this case. So for ammonia, at least we're going to say, look, we know that it has London forces. What about for krypton? What would we say for that? What do you think? Go ahead and put your answer in the chat for what you think the intermolecular forces would be for krypton. And it's okay if you're not sure, a guess is always grand. Ooh, I like that, right? It's a single molecule, right? What if we had multiple kryptons together? What if it wasn't just krypton by itself? Because remember, we're thinking about intermolecular forces. So these are the forces that are between molecules. So assume that I have two or more at least. So I've got at least two, maybe more. So in the case of ammonia, I said, hey, it would have London forces, but the strongest force would be its hydrogen bonds. So if I'm going to put an answer for number one, I'm going to mark hydrogen bonds because that's the strongest of the forces that ammonia would have if I had multiple ammonia molecules together. So yes, it experiences London forces, and yes, there are dipole-dipole interactions, but the strongest of those forces would be hydrogen bonds. If I'm thinking about, right, this atom, right, and if I had multiple atoms together, right, what would be the strongest interaction that I could have? Well, I know that it can't be hydrogen bonds, and I know that it can't be dipole-dipole interactions because I don't have two or more molecules. Nice. I like it. Yep, London is a great choice. So London would be the choice that you would make for this atom by itself. Which then means that if we're thinking about other examples of atoms that are by themselves, right, a London force is a great place to start when we're thinking about the strongest forces that are possible. Okay, let's think about HCl. What do you think about this one? So if you're taking a look, it doesn't meet the criteria for hydrogen bonds, right? Because it has to be OH, NH, or FH. And so in this case, because it's HCl, it can't be a hydrogen bond. So that cannot be the strongest intermolecular force. But, right, is there a significant difference in electronegativity? So because there's a difference in electronegativity, the strongest would be dipole-dipole interactions. So for HCl, I would identify dipole-dipole interactions as the strongest. What about F2? So this is one that's worth thinking about and talking about, right? For F2, right, it's got two together, but they're symmetrical, right? So there should not be any dipole-dipole, right? It would be London forces because the strong dipoles would cancel out, right? And so in this case, we just have London forces. That would be the strongest that we would see for our diatomic gases like F2 or H2 or Br2. Those are always going to be London forces. Okay, let's think about a molecule that's a little bit more complex. So potassium permanganate, or KMNO4. So this one is a little bit trickier right? Because we have to remember that this molecule is actually an ionic bond. So where are the ions? Well, in this case, I have a K plus ion, and I have an MnO4 minus anion. So my K plus cation and my MnO4 minus anion. So in this case, then, these would be ionic crystal or ionic bonds. Potassium permanganate is actually this really beautiful purple crystal. It's actually so dark that it looks black, but if you were to make a solution of it, it would be a very, very deep purple. And part of the reason for that is because it forms this beautiful crystal lattice. That is very common when you are thinking about ionic bonds. So a crystal lattice is pretty common. Okay, let's do another one. This one, sodium chloride. What do we think for sodium chloride? Yeah, so its strongest force is going to be ionic. I agree. What about SO2? So if we think about SO2, SO2 is going to be a lot like CO2. The only difference is it's going to have a lone pair on the sulfur. And so in this case, while CO2, its dipoles cancel, in the case of SO2, they're actually going to add because we have that additional lone pair on the sulfur. And so for SO2, our strongest are going to be our dipole-dipole. So we're going to have our strongest interaction will be dipole-dipole for sulfur dioxide. For carbon dioxide, because those dipoles cancel, its strongest interaction is going to be the London forces. So notice these are two molecules that have very similar structures in terms of their composition, but because of that additional lone pair in the case of sulfur dioxide, it's going to have dipole-dipole as the strongest interactions, whereas carbon dioxide would have only London dispersion as the strongest interactions. What about propane? So this is a molecule that's made up of only carbons and hydrogens. So even though it has much more mass than some of the other molecules we've been looking at, what do you think? What, excuse me, what do you think is most likely for propane? In this case, we have to remember that it's only going to be London dispersion forces because there's not a significant difference in electronegativity between carbon and hydrogen. So it's going to be London dispersion forces. So that's true for anything that is made up of only carbons and hydrogens. So in the case of methane, it's also going to be London dispersion forces. Okay, so I want you to take about 5 minutes and see if you can assign 11 through 20. So take a moment, think about the structure, think about what its distribution of atoms would be in space, think about electronegativity, and assign 11 through 20 for the strongest intermolecular force. the really beautiful part about chemistry is that you are building this skill set that allows you to make inferences or decisions based on information that you're observing. The reason why we think this is really important is you could probably create flashcards and memorize this information, right? It might be possible to do that. However, the dilemma that we have is that you're likely going to, at some point in time, encounter a molecule or a structure or a substance that no one has ever seen before. And so your ability to make inferences about that unknown or that new phenomenon is really important. And so part of what we're doing is we're building skills as a scientist, is really thinking about how we use observation and critical thinking to be able to make sense of new information. And the really powerful part about you thinking about your learning strategies is that you can actually apply that and practice that analytical thinking in different ways as you're engaging with the material. So if we go and take a look at our answer key, you should be able to check your work for 11 through 20. So let's talk through these just briefly in order to make sense. So in this case, unlike methane, number 10, number 11 has the presence of a halogen, in this case, chlorine. And chlorine is what means that this molecule is going to have a significant difference in electronegativity, which is why we see dipole-dipole as the strongest intermolecular force. HF is one of those molecules that meets the criteria for hydrogen bonding. So that's the reason why HF would be hydrogen bonding, is the strongest intermolecular force. And then C6H6 or benzene goes back to that rule of if it's only carbons and hydrogens, then the strongest intermolecular force that it can experience is going to be London dispersion forces. NO, so there is a difference in electronegativity between nitrogen and oxygen, and so that means that it's going to have a dipole-dipole interaction. H2SO4, again, because of the oxygen-hydrogen, is going to experience hydrogen bonding. WC, silicone, SiO2, and carbon are all examples of network covalent solids. And we're going to talk about these in a little bit more detail on Wednesday. But there are some materials that are a network of covalent bonds. So they're not so much distinct or unique individual molecules as much as they are literally sheets or long extended networks or chains of individual atoms. And so these are all examples of network covalent solids. Probably the one that you're most familiar with would be like the graphite that you see in a pencil. And so these are all examples of that. N2, well, probably our best inference here is to actually think about the example that we had just a little bit earlier in terms of F2. So F2 is that diatomic gas, and its strongest forces were London dispersion forces. N2 is in a similar position. So my goal for you is that by the end of today, you would be able to feel comfortable doing the ones on the back. So I think that the best way to make these distinctions and decide what types of intermolecular forces are in play is practice. So you've got a whole back sheet for you to do some additional practice with. And I think that it would be a great idea for you to do that before class on Wednesday, because we're going to have a quiz, and one of the questions on the quiz is going to be assigning these types. So that's a great thing to do, practice and prep around. But for the last couple of minutes of class, I want to go back to and talk about what we're going to be covering in terms of discussion this week. So this week's discussion, we're going to be looking at heating curves. So we're going to, on Wednesday, we're going to talk in a lot more detail about the intersection between solid, liquid, and gas phases. And we're going to be working on assigning heating curves and being able to determine when molecules transition between the phases based on the intermolecular forces that are in play. So Thursday's discussion is going to be a really critical one. And then for our last 5 or so minutes of class, I want you to think about your goals, but we're going to be really intentional here and narrow our focus to thinking about prepping for exam 3 and thinking about preparing for your final exam. So you've come a long way in this class. We're in week 14, which is a long way into a semester. What are your top priorities? So when you think about reviewing your material and you understand that the final exam is cumulative, and exam 3 is really going to focus on chapters 6, 7, and 8. Where are your priorities? What are the things that you want to focus on? So I promised that we would be able to talk about the practice exam that I sent out. So let me go ahead and pull that up a minute. And okay. Oh, sorry, folks. Too far behind. Here we go. It's week 14. I want week 13. All right. So, here we go. So, in this, I sent out exam 3 learning outcomes and a practice exam. So let's take a look at the learning outcomes for just a moment. You're like, hey, wait a minute. We did chapter 6 on exam 2, and you're right, but I think exam 3, chapter 6 is just as closely entwined because your ability to do orbital diagrams or electron configurations are all tied into what you're going to be doing in chapter 7, which is the drawing the correct Lewis structures, being able to draw and label the formal charges, as well as being able to draw correct resonance structures and hybrids. And then for chapter 8, this ability to assign molecular geometry and identify polar molecules, as well as being able to assign bond hybridization. So those are our learning outcomes that we're going to be measuring for exam 3. And here are some examples of problems that you are likely to see for your exam 3. And so I think it's really important that you have examples. Being able to do a claim evidence reasoning statement is a likely problem that you will see. So the ability to provide the correct electron and molecular geometry. Being able to identify elements with the following electron configurations. I had a really great question from several folks about this example. And so if, as you're doing this problem, you encounter or find a resource that has this with a slightly different electron configuration, I would love for you to note it here and tell me why you think it's one versus the other. So there's an ongoing conversation in the scientific community about assigning these electron configurations. So if you find an alternate way of representing this molecule, I would love to see it here. Other examples include the difference between sp, sp2, and sp3 hybrid orbitals. So exam 3 is next week. It's the 29th of April. So it's coming up soon. Here's a great example. So you've had to do the analysis of periodic trends that we looked at for last exam 2, but that's something that's definitely going to show up again, is your ability to analyze trends, because we highly value your critical thinking. And then long answer problems are going to look like this. So you're going to have Lewis structures, right? And then you're going to make determinations of the polarity or electron geometry or molecular geometry. I am sending back your graded exams for exam 2 today. So once we're done with class, I will be sending those out. So I finally got the last 2 that I was waiting for this weekend. So You will get your graded exams with feedback today, so you'll have the opportunity to take a look at those and review long before you have to take exam 3. Being able to classify substances as covalent molecules or ionic compounds. And then you can imagine, right, that in addition to classifying as covalent or ionic, perhaps you could be asked to determine which intermolecular force, right, is the strongest, say, for example, for a molecule. And then being able to assign formal charges, being able to draw resonance structures, being able to draw Lewis structures and determine polarity, so which is a polar molecule versus which is not a polar molecule. And then we also have problems that are very similar to what we've studied for chapter 1 through 4. Again, it's a cumulative exam, so you could potentially be asked about a stoichiometry or a balancing equations problem. And then here are some examples of being able to draw Lewis structures or explain why you could form certain Lewis structures but not others, and then the assignment of bond hybridization. So this is an overview of your practice exam. I think that probably the best use of your time as you're kind of thinking about this week is the following. So I've had Alex as open pie for you, and I think that for some of you, you're all caught up and you're good to go there. In that case, if you're caught up on Alex, then I would spend your time doing practice exam 3 or working on the material for chapter 10. If you haven't caught up with Alex, then I would make that your first priority because this is one of the last open pie Alex windows that we have, and those are great problems to review to get you ready for exam 3. And then last but not least, I think if you're in this space, you're like, oh, I'm just behind, then probably what you want to do is make a plan. So think about the remaining 3 weeks that you have and think about the fact that there's a distribution of points in terms of this class. If you're not sure what those are, you can always take a look at the iLearn course because if you take a look at the top, you can always find the syllabus, and in the syllabus it has the distribution of grades. I believe that an email went out saying that you would have options in terms of credit, no credit, or grades for a course. And so that is your choice. I'm more than happy to talk through the implications of that with you if that's something that you're wondering about. But the minimum passing grade for credit, no credit would be a C-. So you have to get at least a 70 in the course. And that requires that you get a passing grade on your final exams. Just because of the point distribution that's there. So that being said, we've got some work that we're going to do. I want to make sure you have the time to kind of think about and strategize your next steps as you're going into exam 3. And then our big goal next week is that we're going to do a little bit more review and revision to get you set up for success for exam 3, but we're also going to start thinking about how we're going to review and get ready for your final exam. So if you think about kind of our next steps and where we're at and what's happening next, so we're going to wrap up chapter 10 on Wednesday. And then next week, we're going to do some review and we're going to make sure that you're ready for exam 3. You'll have the opportunity to sign up for windows of time similar to what we've done for exam 2 in terms of when you want to work on the exam. And then we'll talk about the structure and format of your final exam. And then in no time at all, it will be the end of the semester, and hopefully we'll have the chance to connect for Chem 111 next semester. So I'm going to hang out here if you've got questions. We are done with class. Don't forget to make sure that in your own notes you've reviewed the kind of last 5 minutes of class. And then we'll finish up with chapter 10 on Wednesday, and then we will be done with all new material for this semester. So if you are thinking about other pieces that you're like, hey, I have questions, or there's something for your lab, I'm more than happy to help with that. I don't know what the structure is for lab this week. You would have to check out the syllabus for your lab course. I believe that there is prep that they're doing for your final lab exam, but I'm not sure what that is. I haven't checked this weekend. And then I think other than that, if you've got everything you need, you are good to go. I hope you have a wonderful day. And otherwise, I will hang out here and happily answer any questions if folks have them.
Dr. Corinne, I have a question about the intermolecular forces.
Go for it.
So for SO2, how do we know that its dipole-dipole attraction is stronger than its London forces?
So in this case, if you have any dipole-dipole interactions and they don't cancel because of symmetry, they're always going to be stronger than your intermolecular forces in terms of London dispersion forces. Okay, and so if I go back up, it was a long time away, but if I go back up here, anytime I have dipole-dipole, oops, sorry, I didn't mean to move that. It's going to be stronger typically than what I see for dispersion. There's a little bit of overlap here, but for the most part, it's always dipole-dipole is always going to win out. So if you have a difference in electronegativity, then dipole-dipole will be stronger than your dispersion forces.
Yeah, thank you.
Ooh, so determining if a compound is polar. That's a great question. So anytime there's a difference in electronegativity and those are shared and they're shared unequally, so either because of a lack of symmetry or because there's a difference in electronegativity, then it's going to be a polar molecule. So if, say, for example, we look at these two, we talked about this a little bit, right? There's a difference in electronegativity between carbon and oxygen. But in this case, right, that difference in electronegativity faces in opposite directions, and so it cancels out, in which case there's no net dipole moment, so this is a non-polar molecule. Whereas if I think about water and the fact that I have two dipoles, but in this case they don't cancel out, they add together, then this is a molecule that has a molecular dipole moment, and so it is going to be polar because there is that uneven distribution of electrons. So essentially, anytime a molecule has a net dipole, it's going to be polar.
Corinne, I have a question.
Go for it.
So for the London forces, I was looking through, like, when you showed the answer key, but I'm not